Section 4.4, page 3. The last example we'll do, example 2, and now it says steps A through G. So question A is always asking about the domain. When it comes to the domain, remember we're looking to make sure that we have a denominator that does not equal 0. We don't have any radicals or logs. So the denominator does not equal 0. Well, we find it by actually setting it equal to 0, or in this case, you could just think of adding 1 to both sides. So the domain is anywhere that x is not equal to 1. So we can go from negative infinity to positive infinity so long as 1 is excluded. So stop at 1 and start again at 1, which is why we have these round parentheses. Next, we want to find the intercepts. We tend to start with the x-intercept by setting the function equal to 0. In our case, you could just say it's only 0 when the numerator is 0, so therefore x is 0. Or because you may get a more complicated function, maybe think about cross-multiplying so that you have 0 times your denominator, and in our case, an invisible 1 times the x. 0 times anything is 0. So we can see that x equals 0. And when I plug it into my original function, I get an output of 0. So I have an x-intercept of 0, 0, which automatically is going to be a y-intercept, but let's make sure there aren't other y-intercepts. Here, we let x equal 0. Oh, well, that's actually how we just got the last output. So yeah, that was our only y-intercept. Now we'll check for symmetry. So we go ahead and plug negative x wherever the variable was, and simplify. Well, in our case, you could think of factoring a negative kind of out of the numerator, but that's it. Since this is neither equivalent to the original question nor negative of the original question, right? Because this wasn't negative in the denominator, we have no symmetry. I think I just went ahead and wrote none. When you look at our picture, since it's already graphed for us, you might argue there looks like some first and third quadrant symmetry, but it's not symmetric about the x and y axes. So it is looking symmetric about some different angles, but we only discuss odd and even symmetry. So next I'm looking for my asymptotes. So my horizontal asymptote is when I take the limit as x goes to infinity of the question. Well, if we ever have x goes to positive or negative infinity, we divide everything by the largest variable exponent in the denominator. So in our case, just divide each term by an x. X divided by x is 1. X divided by x is 1, and minus 1 divided by x is just a fraction. I still needed the limit, but now I can go ahead and plug infinity in, which is why you don't see the limit in front. And remember, 1 over the world's largest number is basically 0. So this simplifies to a positive 1. And when we're talking about a horizontal asymptote, we're talking about the height of the graph. So the graph will reach a height of 1 way out in the infinities. And even with negative infinity, this still is going to tend towards 0. So that's why you'll notice that if this is my origin, right, over here at positive infinity, I have a height of roughly 1. Maybe it should be a little bit flatter. And over here at negative infinity, you can see I have this height of roughly 1, assuming my graph is going that route. So horizontal asymptote, I just have 1, y equals 1 in both the positive and negative infinity directions. For a vertical asymptote, this is when you take the function, not its derivative, and simplify. This does not simplify. You set the denominator equal to 0, but when we set this equal to 0, we get x equals 1. So I have this vertical asymptote, which you can see right here at 1. Now remember, 1's not in our denominator. That's why vertically, we're going to find out my graph is getting really close to 1 on both sides of 1, but it never will actually reach that point. At this point, I didn't know, right? It could have felt like it went like this, right? So I don't have enough information to know that it was headed down and up, but we will find that out shortly. So after getting all of my asymptotes, I'm ready to talk about intervals of increasing and decreasing. They're dependent upon the critical number. This is based on the first derivative. I was not given the first derivative. So I need to recognize this is a quotient rule problem where I'm going to take the derivative of the numerator, which is 1, times the denominator, always minus, and then it's the derivative of the denominator times the numerator. So I've got my 1 times x and my denominator squared. Simplifying my terms, I recognize that a positive x subtracts with another x, and so I've got my derivative. The critical number is when the top equals 0. There's no variable, so there is no critical number. From that, when does the derivative not exist? When the denominator equals 0, which is when x equals 1. But, right, I don't have a critical number because 1 is not in my domain. But I still need that 1 to figure out intervals of increase and decrease. This graph went from negative infinity to positive infinity with my only critical number in the middle. This gave me everything to the left of 1, everything to the right of 1. I'm going to come to my first derivative and plug in a test point for my first interval. So remember, I'm going to the derivative, which is this function. So when I plug a 0 in, I'm going to have a negative on top, and this is going to be squared, so this is going to be a positive. Negative divided by positive is negative, so I have a decreasing region. Same thing, when I plug in a number from the second region, I'm still going to have a negative in the numerator. 2 is going to give me a 1, but 1 squared is still 1. I basically have the same thing. I still have a decreasing function. So this function is decreasing essentially to the left of 1 and to the right of 1. So I have neither a max or a min. Local max, none. Local min, none. But for decreasing, it was the 2 regions I found where I don't have any increasing regions. And then lastly, we wanted to do an inflection point to discuss concave up and concave down. Now I've got this first derivative. I had to find myself here. And instead of doing a quotient rule again, I don't have a variable in the numerator. So let's go ahead and bring the denominator up using a negative exponent. So now when I go to take the derivative, I can go ahead and bring that negative 2 out front, subtract 1 from it, take the derivative of the inside because of a chain rule, and negative 1 times negative 2 is positive 2. Bring my negative exponent term down below. And an inflection point is when this equals 0. It will never equal 0. But I need to discuss concavity. So here's the other piece. Setting the denominator equal to 0, which I'll find out occurs when x equals 1, is not an inflection point because it's when my second derivative does not exist, but it will help me find concavity. Notice, remember, positive 1's not even in the domain. But if I now break my graph up into everything to the left of when the second derivative doesn't exist and to the right of when the second derivative doesn't exist, I can test a point in the region. And, well, this is always going to be positive on top, but plugging a 0 in the denominator because it's cubed is negative. So I'm going to have a negative, therefore concave down region. So I have this general shape. When I plugged a positive 2 in to get a positive cubed, I get a general concave up shape. The thing to recognize with concave up and concave down is that the slope is tending in that region. So let's go back to how, and again, I should have written those 3 answers in. How am I going to graph this? Well, I usually graph by starting with my x and y intercepts. I only had this 1 point. Then I come to my local max and mins. I just moved the answer box. I come to my local max and mins. I don't have any local max and mins, so there's nothing else to plot. But I do know my horizontal and vertical asymptotes. So here's what I know. If this point's down here and I have a horizontal asymptote of 1, I can't cross this dashed line, but I am going to get really close to it. So I knew right away I had this. Same thing happens here. I knew I had to get close to that line, so I've got this general shape. Now over here, I didn't know what happened, right? I could have had something that looked like any of these other pieces. So what I would do is just find some other point on the graph. Like I decided, let's plug in 2. So do I show the math on this anywhere? No. But notice if I plug 2 in here, 2 all over 2 minus 1 is just 2 over 1. So I get 2 out. So I knew I had the point 2, 2. That's how I knew, hugging my asymptotes, I had to have this shape. In terms of concavity, it doesn't feel concave down in the third region, but if you kept doing these tangent lines, they would continue to get smaller and smaller.